Hi there everybody, within the whole universe, I hope that everything is fine, and I'm a Russian man who brings value with my own experience, and today we're gonna talk about the data structures. What are they, and why do we have them, and where do we implement them? And let's talk. It will be about byte, short, in, long, float, double, char, string, boolean, array, tuple, container, reference, pointer, handle, plus other features. We'll talk about them. First of all, byte, short, in, long. What's it? It is an integer type of data. For example, it is 3, 4, 5, 6, 7, 8, 9, 10, minus 2, and etc. It could be byte, it is for 8 bits, also short for 16 bits, and byte short int for 32 bits, and also long, it is for 64 bits if we will look at them in Java, for example, because in different languages they could be stored with different types of bits of information. Also, float double, what is it? Float and double, it is precision numbers, floating point number, fixed point number, and they could be with different precisions. Also, char, it is char character, yes, it is for the character symbol A, B, C, D, E, F, G, X, Y, Z, and etc. It could be. Also, wow, it's with rhyme, did you hear it? It could be X, Y, Z, okay, and also we have boolean. It is for true or false, false or maybe 1 or 0, yes or no, and it is about this. Also, we have string, it is the specific sequence of characters. For example, a word, it is a sequence of a space W-O-R-D, yes, sequence, and we have them. Also, arrays, it is, like we described right now, it is strings, but it could be with numbers also, with floating point number, with integer numbers, and etc., whole numbers, yes. Also, we have tuples, it is almost arrays, but not arrays. Also, we have references, and pointers, and handles. They are almost it is different names of them, and they are pointing to the specific sequence of zeros and ones in your sequence of inside of your computer, inside of your data, inside of kind of machine code. It points to this specific thing where it is stored, for example. Yes, also we have trees, we have heaps, we have ropes, we have hash tables, we have TRIE tree, and also binary tree, ternary tree, KR tree, heaps, VList, A list. Also we have a control table, routing table, symbol table, piece table, light map, dope vector, leaf vector, and different types of them. We'll dive into them right now. And about trees, it is actually, we're going there. Binary tree, it is 2 things, ternary tree, it is 3 things, KR tree, it is K number of children. Also have parent children's, and also have or and tree, also link cut things, and different things of this nature. Also map, multi-set, set, graph, hypergraph, multigraph, and B asterisk 3, B plus 3, B3, and B sharp 3, and other features we have also. Let's dive into them and learn a little bit more about them. It will be our awareness time of data structures. As I said before, we have boolean, character, floating point number, and fixed point numbers, integer, reference, enumerated types too, and a small set of unique named values. Date time, it is to your date and time, what's day is today and what's time is it. Yes, it could be it could show. Also array, and also string array, it is example. Record or structure, it is one more type of composite types. data structures. Union, tagged union is a subset also called variant, variant record, discriminant union or disjoint union. Discriminant means that it is discriminated, means that it is different from others. It is it is something from Latin. Need to Google to it about it. Container, list, tuple, associative array or map, multi-map, set, multi-set or bag, stack, queue, example priority queue, double-ended queue, graph, example tree, heap. Okay, we have them. Also about arrays, we have array, bit field, bit board, bit map, circular buffer, control table, image, dop vector, dynamic array, gap buffer, hashed array tree, lookup table, matrix, parallel array, sorted array, sparse matrix, leaf vector, variable length array. It is all about arrays, so we can look at them. They are different, they are good, and we have some points here, and so we have also matrix here, yes, and also bitmap, bitboard, bitfield, bitarray, and others. Lists, doubly linked, list, array list, linked list, association list, self-organizing list, skip list, unrolled linked list, vlist, as I said before, conc tree list, XOR linked list, zipper, doubly connected edge list, also known as half edge, difference list, free list. Okay, binary trees. AA tree, AVL tree, binary search tree, binary tree, Cartesian tree, conc tree list, cell left child, right sibling binary tree, order statistic tree, pagoda. Pagoda, I think that I said correct with accent on the first syllable. Maybe it is on another way, but actually in Russia we pronounce it this way in terms of the temple, for example, yes. And randomized binary search tree, red black tree, rope, scapegoat tree, self-balancing binary search tree, splay tree, T tree, tango tree, threaded binary tree, top tree, trip, WAVL tree, weight balance tree. B trees, B tree, B plus tree, B asterisk tree, B sharp tree, dancing tree, 2-3 tree, 2-3-4 tree, quip, fusion tree, BX tree, A list. Yes, as it was said before, V list, A list, here they are. Heaps. Heap, binary heap, B heap, weak heap, binomial heap, Fibonacci heap, F heap, Leonardo heap, 2-3 heap, soft heap, pairing heap, leftist heap, trip, beep, skew heap, ternary heap, D-array heap, Brodel queue. Interesting fact that it is D-array heap, and we have also K-array tree, somewhere it will be. Yes. Also trees. Tree, data structure, radix tree, suffix array. It is about different types of lexems we have, and we have different types of morphemes, and also prefixes, postfixes, infixes, suffixes, interfixes, and others. Compressed suffix array, by the way, need to Google, do we have interfixes, interfixes? One moment, interfix. Yes, we have. Interfix is here, interfix, yes, and in phonology, interfix or more commonly linking element is a phoneme which is placed between two morphemes and doesn't have a semantic meaning. And also interfix, but what's different with actually fix? I mean that we have prefixes, infixes. Yes, we have infix. What's the different? Yes, we have infix, and also we have interfix. Also transfix, simulfix, suprafix, disfix, duplifix, circumfix, suffix, prefix. Okay. Okay, let's dive into this. Compressed suffix array, FM index, generalized suffix tree, B tree, Judith array, X fast tree with I, TRIE, Y fast TRIE, in the third position it is I letter, Merkle tree, C tree, multi-way trees, ternary tree, K-array tree, and or tree, AB tree, link cut tree, SPQR tree, spaghetti stack, disjoint set data structure, union find data structure, fusion tree, enfilade, exponential tree, Fenwick tree, Van Empt Boas tree, Rose tree. Good. Next, space partitioning trees, segment tree, interval tree, range tree, bin, KD tree, implicit KD tree with dimensional k-dimensional tree, min max KD tree, relaxed KD tree, adaptive KD tree, quad tree, oct tree, linear oct tree, z order, UB tree, R tree, R plus tree, R asterisk tree, Hilbert R tree, X tree, metric tree, cover tree, M tree, VP tree, BK tree, bounding interval hierarchy, bounding volume hierarchy, BSP tree, rapidly exploring random tree. Okay, application specific trees, abstract syntax tree, parse tree, decision tree, alternated decision tree, minimax tree, expectiminimax tree, expectiminimax tree, finger tree, expression tree, log structured merge tree, lexicographic search tree. And here is hash-based structures. Bloom filter, count main sketch, distributed hash table, double hashing, dynamic perfect hash table, hash array map tree with TRIE, with I in the third position, hash list, hash table, hash tree, Kurdi, prefix hash tree, rolling hash, min hash, quotient filter, C3, quotient filter, Bloom filter, they are the same. I mean that the same part, the same second name, the same second word, I mean. Graphs, graph, adjacent list, adjacency matrix, graph structure stack, scene graph, decision tree, binary decision diagram, zero suppressed decision diagram, and inverter graph, directed acyclic graph, propositional directed acyclic graph, multigraph, hypergraph. Light map, winged edge, quad edge, routing table, symbol table, piece table. We have them, okay, and we can learn more about, let's pick the quotient filter. I think it will be nice to read, and actually we've read all the list. A quotient filter is a space-efficient probabilistic data structure used to test whether an element is a member of a set, an approximate membership query filter, AMQ. A query will elicit a reply specifying either that the element is definitely not in the set or that the element is probably in the set. The former result is the definitive. For example, the test does not generate false negatives, but with the latter result there is some probability epsilon of the test returning elements is in the set. Element is in the set. Element is in the set. Element is in the set. Okay. When in fact the element is not present in the set, for example a false positive, there is a trade-off between epsilon, the false positive rate, and storage size. Increasing the filter's storage size reduced epsilon. Other AMQ operations include insert and optionally delete. The more elements are added to the set, the larger the probability of false positives. Probabilistic data structures, Bloom filter, count min sketch, quotient filter, skip list, random binary trees, tree, rapidly exploring random tree, randomized algorithm, hyperlog log. Okay, let's take a look. Filter, no, filter, yes, false positive, okay, storage. It is with different types of errors, I think so, with RCA or something, maybe. Okay, it is a hash table actually. That we have specific data structure, quotient filter. So it was nice to read it. Now we know them more. And why do we use them a lot? Why do we have all the different types of data structures? Because when we use a specific type of the data, it will be better to the computer to use the specific storage for them. Kind of imagine that you have boxes and you have the box with integers, the box with it, the box with it, the box with it. For example, the box with integers, the box with words, the box with toys, the box with names of different people. As for example, we have words, yes, specific words, and also names for specific people, yes, and we have different boxes, numbers, words, toys, and specific names. And for each of them, we have specific indexes. indices. For example, we have indices number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, and also we have word 1, word 2, word 3, word 4, word 5, word 6, word 7, and etc. Also we have toy 1, toy 2, toy 3, toy 4, toy 5, toy 6, toy 7, and etc. Also have names. Name 1, name 2, name 3, name 4, name 5, name 6, name 7, name 8, and etc. Also, for example, we have a box of welding. Welding 1, welding 2, welding 3, welding 4, welding 5, welding 6, welding 7, and etc. We have indices of them, and it will be faster to recall the function, to recall the data, to recall the specific storage where it is stored, the specific thing, specific container, specific table or something, to recall some entity, some things from the computer. It will be faster if we will recall like not the word not the word 137, but we will recall toy 23. It will be faster because don't need to kind of go to this upper layers. For example, yes, 23, it means that we will use 32 bits of information. 32 bits of information, it is the 2, 4, 8, 16, 32. It is 5 bits of information. But if we will use 64 bits of information, it will be 64 variations, then it will be 6 bits of information. 7, it will be already 128, and to store something that 123, we need a lot of, we need 7 bits of information. But for the, if we need to recall, for example, 7, the 7, only a number of 7, then we need only 3 bits. Only 3 bits to store the 7, for example. But it all depends. It was kind of imaginative situation. Yes, ideal kind of that we right now count the specific example. Yes, kind of idealistic or something. Yes, a model, abstract model. And if we have the bigger number, we need a bigger storage for them. But it will be better to use kind of to divide them to specific storages for specific data structures. That's why we use different data structures and different types of data structures for specific purposes, because by using for a specific purpose, you don't need to use a lot of memory. You use specific optimized number of memory in your computer, specific optimized number of things inside of the space, kind of use less space, and it means that you use it effectively, and you will be more productive and your results will be faster, and maybe even by time you will do this faster in some cases. Okay, so thank you a lot for watching. Improve Slow Daily, go forward, learn big O notation, and have a good day. Bye.